Now looking at, we have completed this part. We will be talking about boundary conditions and wave equation here in today's class. So what we want to start off with is, what I want to start off today is to write down the electromagnetic wave equation, electromagnetic, the basic 4 equations for electromagnetics, which is your Maxwell's equations. We had derived Faraday's law, or rather we had stated Faraday's law, which says that closed loop integral E dot dl is minus d by dt of surface integral B dot ds, essentially which said that whenever there is a change of magnetic flux, there is an induced EMF. We had also written down Ampere's law, and we discussed about Ampere's law quite a bit yesterday. Ampere's law, which where we talked about conversion from electric field to magnetic field. So we talked about loop integral H dot dl. You can induce magnetic field from a steady current, which is surface integral J dot ds, or you could induce magnetic field from a time varying electric flux. So you had d by dt of surface integral d dot ds. So time rate of change of electric flux can give rise to magnetic field, steady current also can give rise to magnetic field. Now after that we derived Gauss law from Ampere's law and Faraday's law. We applied actually Ampere's law on a closed surface, and we derived that closed surface integral of d dot ds, which is the net flux emanating from a closed surface. We said that is equivalent to charge enclosed by the surface, which is volume integral of rho dV. We will also write it as Q enclosed. Another way of writing this is closed surface integral of epsilon E ds, or epsilon E ds is equal to charge enclosed divided by epsilon. This epsilon becomes epsilon naught when you are in free space. Both representations are correct. One more law of which does not carry any specific name is Gauss law in magnetism, which states that closed loop integral, closed surface integral B dot ds is equal to 0. So there is nothing called as magnetic charge. These two laws are kind of symmetric between electric and magnetic field, and these two are the parallels. Now these are integral forms of Maxwell's equations. Now you could also have, so last class we discussed when do we use the integral form. I said we will use the integral form when we want to apply Maxwell's equations at a boundary, because none of these equations specify that it has to be in a applied only in a specific medium. So let us say I have a boundary, and when I say boundary, it means that I have, let us say, medium 1 and a medium 2 and a surface that separates medium 1 and medium 2, and I can apply Maxwell's equations at the boundary. Now what do you mean by applying at the boundary? It means that, let us say, let us pick up the first equation, Faraday's law, E dot dl is equal to, we just wrote the Faraday's law, it is minus del by del T of surface integral of B dot ds. Assume that we want to apply, let us say we want to apply this on a boundary. Now why do I want to do this? I want to do this to find out what is the electric field. Let us say if the electric field in medium 1 is E1, I want to know what is the electric field, I want to find out what is the electric field in the second medium. My electric field in medium 1 could be in this direction, let us say, I want to actually know what is E2 in this direction. Is it going to be the same? Is it going to be different? Medium 1 and medium 2 are different. When you say they are different, you have to ask yourself the question, how are they different? So, I am saying that the epsilon for medium 1 is epsilon 1, epsilon for medium 2 is epsilon 2, mu for medium 1 is mu 1, mu for medium 2 is mu. So, they are different in terms of epsilon and mu, the material properties, the material response. Epsilon and mu are actually the material response of the medium to electric and magnetic field. How do I do this? How do I calculate this? Now, electric field could be in an arbitrary direction. So, what we are going to do is we are going to apply Faraday's law, not just for medium 1, not just for medium 2, we are going to apply Faraday's law in the interface between medium 1 and medium 2. Because while defining Faraday's law, I never said that it does not work for an interface. So, let us say this is the interface and this is medium 1 and this is medium 2, and let us say I have an electric field this way, and I actually want to calculate what is the electric field in medium 2, or essentially saying that I have a region of electric field and I am bringing a glass piece, for example, in that region of electric field. I want to know how does the electric field bend inside the glass piece. So, for that I am going to use Faraday's law. So, how do I use Faraday's law? What is the left hand side of Faraday's law? It says loop integral E dot dl. I need to have a loop. Now, where do I put the loop? If I put the loop inside medium 1, I am not going to get any specific benefit out of it. It will just tell me that as the magnetic field inside across the flux through the loop changes, I will have an induced EMF. That is not benefiting me. So, I will take advantage of the fact that I have not defined Faraday's law for a specific medium, and I will keep my loop in between medium 1 and medium 2, exactly in between medium 1 and medium 2. Let me call this loop as A, B, C, D, and the loop integral, let me define the direction of the loop. This is the direction of the loop integral. Okay. So, I am going to apply Faraday's law onto this loop, apply Faraday's law in the loop A, B, C, D, A, in that direction. So, how do I apply Faraday's law? Let us pick the left hand side. What is integral E dot dl? This is a line integral, and it is a closed line integral, which means I have to apply the line integral all across the loop. And what is the meaning of line integral? If I have the loop is in this direction, if my electric field is in this direction E1, E dot dl, dl is in this direction. So, E dot dl is a component of the electric field along the loop. Now, the component of electric field along the loop would mean component of electric field along the surface, I would have the electric field this way. I am trying to find the electric field component along the surface. Let me call that as the tangential component of electric field, tangential to the surface, parallel to the surface. So, this let me call as E1 tangential. The component of, so if this angle is theta, E1 tangential is nothing but E1 cos theta. Okay. I do not want to define a specific theta, which is why I am just saying it is a tangential component. And I can also think about a normal component, which is the y component of, or component of E in a direction normal to the surface. So, your reference is the surface. If this is my surface boundary, if this is my electric field, tangential component is a component of the electric field along the boundary, normal component is a component of electric field perpendicular to the boundary. So, this is my E1 normal, and of course, E1 normal is E1 sin theta. Now, if I were to apply the loop integral, then this dot product is E1 along the AB direction, which is a tangential component of electric field. I have to multiply it with the length, integrate it over the length. So, let us say the width of the loop is W. So, that integration is going to give me W E tangential. I have to write this integration. This is a closed loop integral. So, I need to integrate this AB E dot dl from A to B, plus I have to integrate from B to C E dot dl, plus I have to integrate from C to D E dot dl, plus I need to integrate from D to A E dot dl. Only then I will complete a loop integral. I have to integrate in this path, third path and fourth path. The first path has already given me an answer. It gives me an answer which is E1 tangential, and this length integral, when you integrate over this entire length, will give me W. Plus, look at the second path and the fourth path, B to C and D to A. They are equal and opposite with each other because everything else remains the same, only the direction has changed, which means that these two terms will actually cancel out. Now, these two terms will cancel out actually not because they are in opposite direction. These two will cancel out because you have the angle as 90 degree. So, that will get, that dot product will get cancelled out. Now, you have other remaining integral which is opposite to each other. So, I will get minus W, and here my direction of dl has changed. So, which is why I have a minus, and the field in the in the medium 2 is actually E2. So, this is E2 tangential. Let us not cancel out this contribution. Let us just write this contribution as plus E1 dl. It is in the downward direction. Normal component is in the upward direction. So, this, let us say this width is d, or let us say this height is h. Let me just write this as minus h E normal component, or the first E normal component in the first medium, because it is here. In fact, this whole of h I can divide into h by 2 in medium 1 and h by 2 in medium 2. So, it is h by 2 due to first field minus h by 2 due to the second field. Again, this integration will be plus h by 2 E2 in the first field plus h by 2 E1 in the second medium. So, essentially what I did was, this component I wrote as a tangential component, but the width along the width direction, or rather along the height direction, I divide this into h by 2 and h by 2. Half of it is experiencing a field E1, half of it is experiencing a field E2, and the component of E1 in the normal direction is the normal component. So, I have the normal component. I got this negative sign because my E1 is along increasing direction, positive right northeast direction. So, my component is in the component of the normal component of E1 is in the direction pointing up, whereas the loop is pointing down, which is why I had a minus h by 2. This became h by 2 because I divided them into two media. One media is experiencing E1, the other media it is experiencing E2. Now, what I am going to do is, I am going to calculate integral E dot dl. I want to know what is happening at the surface. So, how do I reach the surface? I started with a loop. That loop will converge to the surface only when that h tends to 0. So, I am going to put the limit that in the limit as h tends to 0. So, in the limit as h tends to 0, I will not have this h, I will not have this h, I will not have this h, I will not have this h. In that limit, my integral E dot dl is simply W times E1 tangential minus E2 tangential. Now, note that this term did not change because as h tends to 0, it is only the height that got compressed, the width remained the same. Now, this is the left hand side of Faraday's law. What about the right hand side of Faraday's law? The right hand side is minus d by dt of surface integral of B dot ds. Now, as h tends to 0, area tends to 0. You were trying to find out the flux through that, you were trying to find out, the right hand side will try to find out how much is the flux through that coil, right. So, that flux is going to be 0 because in the limit as h tends to 0, you have shrunk that coil and the coil does not have area anymore, which implies the right hand side is 0. So, what does Faraday's law give us on that loop? It tells me that W times E1 tangential minus E2 tangential equal to 0, or this simply implies E1 tangential is equal to E2 tangential, because there is no reason for W to be 0. W is not 0 in general. The loop is not having 0. If it is having a 0 length, it simply means that there is no loop. So, this gives us the first boundary condition, that the tangential components of electric field on either side of the boundary is. Now, to find out the second boundary condition, so this is the first boundary condition. This is the boundary condition. We are trying to find out the boundary conditions for electric field. Okay. Now, how do I get the boundary condition for the normal component? This relation just says that only the tangential components are equal, which means that if I have an electric field in this direction, the component of electric field along the x direction in both the media are the same. So, if this is medium 1, if this is medium 2, all what this relation says is that the electric field will have the same component, this length is the same. It does not say that the vector is at the same angle, because I could have a different component along the y direction. I still do not know what is the relation between the components in the y direction. If the component along the y direction has changed, then it means that my vector is going to turn at a different angle. This could be E1 and this could be E2. But I still do not know what is the relation between these vertical lines, I mean the length of along the vertical, but I know that the length along the horizontal, this length are identical. These lengths are identical. Now, what about normal components? Now, to be able to find out what is happening to normal component, what we are going to do is, we are going to apply Gauss law. See, always remember that when you want to get the tangential component, you are trying to find out the component along a line. So, a line integral will help. Whereas, if you are trying to find out the normal component, you are trying to find out a component along the surface, because along the surface normal, right. Remember, line integral told the effect of vector over a line, whereas surface integral tells us the effect of a vector across a surface, and the surface is uniquely defined by the surface normal. So, if you want to do a surface, if you want to get the normal component, you should use surface integral. That is the hint. Okay. So, I am going to use Gauss law, which says that the total flux d dot ds emanating from the surface is equal to the charge enclosed by the surface. Okay. So, I can say that this is equal to volume integral rho dV, okay, where rho is the volume density of charge. So, to apply Gauss law, I need a surface, and what surface am I going to use? I am going to use a cylinder. I am saying that I have a cylinder which is placed between the two media. So, you think about it as this is the boundary that separates two media. I have a cylinder like this, half of it is in one media, the other half is in the other media. Okay. So, this is my medium 1, this is my medium 2, I have the electric field E1 and I want to know what is E2. I already know that the tangential x components are the same, the component of the electric field along the boundary is the same. Now, what about E normal with respect to E normal 2? So, I apply this Gauss law. It says that I need to calculate this closed surface integral, and I am going to use the same trick. I am going to say that this surface normal, of course, surface is always outward normal. So, this is ds here, the surface normal is ds here. I am going to apply Gauss law in the limit that h tends to 0, which means that surface is reducing to 0. Then d dot ds would simply mean d1 normal component. It is a normal component. D dot ds is the component of d along ds, and ds is outward normal. So, that is a normal component of d. So, d1 dn, d1 normal component of d in the first medium plus, that is only the top surface. What about the side surface? I do not have to consider the side surface because my h is going to be 0. I am going to calculate this in the limit as h tends to 0. So, then I am left only with the bottom surface. I know that the bottom surface, the surface normal changed its direction. From the positive y direction, it changed to negative y direction, which means that the surface normal would be minus d2n. Of course, I have to integrate over the area. So, let us say A is the area of the surface. This must be equal to the right side. Now, what is the right side? The right side should tell me what is the charge on the surface, because as h tends to 0, it means that as h tends to 0, it is possible that I have a charge accumulated on the surface, because I have no reason to know. It could be a plate of the capacitor for all what you know. So, there could be charge on the plate of the capacitor. This boundary could be the metal plate of the capacitor, and I could have charge in the plate of the capacitor. So, it means that I need to find out what is the charge Q on the surface. Now, if rho s is the surface density of charge, which means that rho s is the charge per unit area, then Qs gets related, gets related to rho s as A times rho s multiplied by Q multiplied by A gives me total charge, because rho s I have assumed it is the charge per unit area. So, if I substitute that, all my A's get cancelled. I get a simple enough relation d1 normal minus d2 normal is not 0, but it is equal to Q, and this is my second boundary condition. So, my first boundary condition which said that the tangential fields are equal, the second boundary condition says that d1 normal minus d2 normal is Q. How do I write it in terms of E1 normal and E2 normal? I know that d is equal to epsilon E. So, d1 normal is epsilon 1 E1 normal minus epsilon 2 E2 normal is equal to Q, or this, sorry, it is not Q, it should be rho s, because my area got cancelled. So, this should be rho s. If rho s is equal to 0, which means I am taking a surface where there is no surface charge, then epsilon 1 E1 normal must be equal to epsilon 2 E2 normal. The normal components are not equal, but they are different, and the difference can find out the normal component E2 normal. It is dependent on the relative permittivity, which means that, as I drew earlier, if E1 tangential is the tangential component and E1 normal is the normal component, then the tangential components, these components are equal, whereas these two are unequal. They are unequal, and they are unequal by a number which is given by epsilon 1 by epsilon 2. So, if your epsilon 2 is greater than epsilon 1, then your E2 normal, which is equal to epsilon 1 by epsilon 2 times E1 normal. This means that if epsilon 2 is greater, then E2 normal is actually smaller than E1 normal, which means that E2 normal has a smaller y component, which means its slope is actually increasing. So, this is the boundary condition for electric field. So, surface integral E dot dl is equal to minus del by del t of, sorry, loop integral E dot dl is equal to minus del by del t of flux, change of magnetic flux. This gave me a boundary condition that E1 tangential is equal to E2 tangential. Similarly, closed surface integral d dot ds, the net flux emanating from the surface is equal to the charge enclosed by the surface. This gave me a boundary condition which said that epsilon 1 E1 normal minus epsilon 2 E2 normal is equal to rho s. You can similarly apply the same boundary conditions similarly for on a loop and a surface for Faraday's law. How would that look like? Integral h dot dl. Faraday's law said that this is equal to the surface integral j dot ds plus del by del t of surface integral d dot ds. Again you start with a loop and you shrink that loop to with h equal to 0, which means that the flux due to current, conduction current and displacement current both are 0. So you will just be left with this, which tells you that h1 tangential minus h2 tangential is equal to, you will get the current, line current, because even though you reduce the surface to 0, you could still have a line current passing through it. So this would be the line current, and the Gauss law, which says that the net magnetic flux is equal to 0, you apply the same thing there, it will give you B1 normal minus B2 normal is equal to 0. That will give you the right hand side equal to 0. So this is this summary of all the boundary conditions. What we will do is we will work out application examples for this boundary conditions, but before that let us look at one more aspect, these Maxwell's equations, and that aspect is about the differential form for Maxwell's equations. So we saw these are the integral forms and these are useful to derive these boundary conditions. This is going to tell how the electric field and magnetic field is going to behave when there is a change in medium. Now, but let us say I want to know in a homogeneous medium how the electric field and magnetic field is going to behave. So that is given by the differential form of Maxwell's equation. Now what is this differential form? Now this differential form, I should be able to write it as d by dx or del by del x, del by del y, del by del z. How do you get the differential form? You go back to what we learned. We learned connecting divergence and surface integral through what is called as the divergence theorem. In the first class, we talked about divergence theorem and also Stokes theorem. So this is Gauss's divergence theorem, which says that volume integral of divergence is equal to closed surface integral of the same vector. This should be d because you have used the same vector d. And Stokes theorem says that surface integral of a curl is equal to line integral of dl. So we are going to use this two theorems to get to differential forms. So we are going to use Gauss's theorem. Said that if I take the divergence of a vector and integrate it over volume, that is nothing but closed surface of A dot ds, and Stokes theorem mentions that if I take a curl of a vector and integrate it over an area, I do a surface integral, my answer is loop integral A dot dl. So if I pick any of these closed loop integral, I can replace this loop integral, this is of the form A dot dl, I can replace this as, so I can replace in Faraday's law, I can replace that integral E dot dl as surface integral curl of A dot ds, and the right side is minus d by dt of surface integral B dot ds. Now if I interchange the differentiation and integration, this would mean that minus integration of d by dt of B dot ds, which I can do without loss of any generality. Now both of them are, if I do the integration on the same surface for the left hand side and the right hand side, it means that I can bring this under the same integral and say that curl of A, sorry, it is not curl of A, it should be curl of E because my vector is E. So this is curl of E dot ds, and ds is common. So minus del by del t of d by dt becomes del by del t because it has moved its place. It means that I could have B changing with time or surf S changing with time. Both will change the flux as a function of time. Del by del t of B dot ds equal to 0. Now this integral uniquely becomes 0 for any surface only when curl of E is minus del B by del. So this is Faraday's law written in the integral differential form, point form. Similarly, I can write curl of H, loop integral H dot dl as surface integral curl of H dot ds, and the right hand side is surface integral J dot ds minus surface integral del by del t B dot ds. Here again I push the integration out and differentiation in, and if I do the same process I get curl of H is equal to J, sorry, this was plus, so J plus, this one is plus, so this is conduction current plus the displacement current. So this is del by del t of D. This is my Ampere's law in the point form. Now I have, how do I apply Gauss theorem now? I have applied Stokes theorem on Faraday's law and Ampere's law and I got the point form. Now how do I apply Gauss divergence theorem? If you look at this, surface integral D dot ds is nothing but volume integral of divergence of A. So I start from Gauss theorem, so this is Ampere's law. Gauss law in the integral form is surface integral, closed surface integral D dot ds, closed surface integral D dot ds was equal to volume integral rho dV. Gauss theorem I apply, I will say D dot ds surface integral is nothing but volume integral of divergence of D dV, and your right hand side is volume integral of rho dV, which means your divergence of D is equal to rho. Similarly, I apply Maxwell's equations for the surface integral of the flux, magnetic flux. This is 0, which implies divergence of B equal to 0. So these are my 4 equations, the ones which are boxed. These are the 4 equations in the differential form or point form. Now, as I said, if you want to solve for electric and magnetic field in a given medium, you will use the point form. If I want to solve for the electric field and magnetic field in between medium. So when do you use point form? You use point form to calculate E, H in a given medium. You use the integral form. You want to calculate E and H at boundaries. Okay, so that's when you use the point form and integral form. Now one small part is remaining, after which we can start working out examples, and that part is derivation of wave equation. You see the 4 Maxwell's equations. Now I am going to write the point form. Del dot D is rho, del dot B is 0, del cross E is minus del B by del T, del cross H is J plus del D by del T. Now, these are self consistent. They are to be satisfied simultaneously, which means that the electric field and magnetic field in a material or in free space should be such that it has to satisfy all the 4 equations. I cannot find electric field and magnetic field in a medium which does not actually satisfy one of these. All of them have to be satisfied simultaneously. So, in a way, if I see, I have 2 variables, which is, and because I know D is equal to epsilon E. So, D and E are not independent variables, and I know B is equal to mu H, which means that B and H are not independent variables. So, the independent variables in the system are actually either you can say E or D and or B and H. And I have 4 equations and 2 variables. So, which means that I can definitely eliminate and find out what is E or H. So, that is what I am going to do next. I start with curl of E is minus del B by del T. I do a curling operation. I take curl of this equation. So, this is curl of Faraday's law. There is nothing that is preventing me from taking the curl of this. Only thing is I need to take the curl of del B by del T also. And curl of this operation can be interchanged. Curl of differential is the same as the differential of curl. So, minus del by del T of curl of B is also going to give me the same answer. And I apply B equal to mu H. So, is equal to minus mu, and let us say I say B is equal to, I have it B equal to mu H. So, I am going to write this because mu is a constant that can come out minus del by del T of curl of H. Now, what about the left side? It is curl of a vector function. Now, curl of a vector function is del dot E minus del square E. This is a result from vector calculus. This can be proved. So, this is minus mu del by del T of curl of H. I know what curl of H is. Curl of H is J plus del D by del T. I am going to write as epsilon del E by del T. Right. So, this, but I know now if I say that, so this is the wave equation in general. Gradient of divergence of E minus del square E is equal to minus mu del J by del T minus mu epsilon del square E by del T square. This is the wave equation in general. But if I choose a medium where rho is 0 and current density is 0, if that is the case, then divergence of E becomes 0. So, I just have del square E equal to, apply a negative sign uniformly everywhere, and this J is 0, this is 0. So, I will just have mu epsilon del square E by del T square. And this is my wave equation. Now, it is called as a wave equation because this del square E actually gives del by it, the expansion of del square is del square by del x square of E plus del square E by del y square plus del square E by del z square equal to mu epsilon del square E by del T square. Now, the left hand side is telling you the variation in space, right hand side is telling you the variation in time. So, essentially the variation in space is linked to the variation in time, and that is why you call this as a wave equation. Now, you remember this is a vector equation because you are operating on E, which is vector quantity. How do you make it as a scalar wave equation? you say that E is, let us say, Ex with x component along Ax along unit vector along x direction, Ey Ay plus Ez Az. Then I can write this as del square by del x square Ex Ax plus Ey Ay plus Ez Az plus del square by del y square of the whole thing plus del square by del z square of the whole thing equal to mu epsilon del square by del t square of the whole thing. And in each of this I will have an Ax component Ex Ax plus Ey Ay plus Ez Az, which means that I actually have 3 equations here. So, I can equate the x component separately, y component separately, z component separately. It means that del square Ex by del x square plus del square Ey by del y square plus del square Ex by del y square plus del square Ex by del z square is equal to mu epsilon del square Ex by del t square. This is a scalar wave equation, because you have taken the components separately and you have them equated. Similarly, you can have equations for Ey component. So, independently the x component, y component and z component are satisfying your wave equation. Similarly, just like how we wrote for the xy component, similarly for Ez component. So, each component of electric field is satisfying the wave equation. It is not just that. So, when you say vector wave equation, you are just saying that the electric field vector is satisfying the wave equation, and now you are saying that not only the electric field vector satisfies, each component of electric field is also satisfying the wave equation. Now, you will also come across something called as Helmholtz equations. Now, Helmholtz equation is a simplified way of writing the wave equation, where you assume that your electric field is in general a position of function and time. You assume that the electric field, the dependence of electric field as a function of time is of the form exponential j omega t, or a sinusoidal. It is a sinusoid, and a sinusoid can be represented as, in the complex number notation, as exponential j omega t. So, I could represent such a field as E. So, this is what is called as a sinusoidal representation. Okay. So, you are saying that, or you call this as harmonic. It is time harmonic, which means that you will have a space dependence, but the time dependence is given by e power j omega t. The advantage of doing this is that when you do del square E by del t square, its first differential, second differential e power j omega t. So, times E times R. So, if I differentiate E as a function of R and t, I just get twice with respect to t, I get minus omega square E a function of R and t, because this is E a function of R and t. So, then what will happen is I can replace, I can write del square E, which is my grad square, is equal to, instead of writing it as mu epsilon del square E by del t square, I can write it as minus omega square E. So, I can get rid of the time differentiation function of R and t. This is also a function of R and t. So, I can write this equation of as del square E plus mu epsilon omega square E equal to 0. This is your Helmholtz equation. The benefit of doing Helmholtz equation is that you are analyzing a specific electromagnetic wave propagation of a specific frequency. Now, if I know the wave propagation for a specific frequency, I can actually derive it for any frequency. Any signal, you can think of it as it can be decomposed into multiple frequencies, and then you can apply linearity and say that, if I know the response at frequency omega 1, I know the response at frequency omega 2, if the net response will be the response at omega 1 plus response omega. So, that completes our portion of what we had committed on each of these Maxwell's equations and the wave equation. So, the wave equation we saw we can derive in terms of vector wave equation, which has derivative in the function of time. But if I am doing the same thing for a specific frequency, I got the Helmholtz equation. Now, I can see that many of, because it was little bit of mathematics, what I can do is now what I can show you before solving problems, I can show you some of the resources from which you can visualize these electromagnetic fields. So, I have one resource here, PHET, which actually is a consolidation of several interactive simulations. It's freeware developed by University of Colorado Boulder, and if you go at click on one of these radio waves and electromagnetic waves. This is the simulation we saw the other day, that we were wiggling the electric field and we were generating magnetic field. You can go and take a look at that. Another example is a very useful resource is Amanogowa. So, you might want to just note down the link here. Now, if I look at, for example, electromagnetic wave propagation, it actually gives you how the solution of the wave equation. So, the red line is actually showing you the electric field, the blue line is showing you the magnetic field, and I can demonstrate the propagation of electromagnetic wave through such simulation. So, you see what is happening when the electromagnetic wave is propagating. The electric field is oscillating up and down. You just focus on the red line. So, the electric field, that red line is the electric field. As the electric field is propagating up and down, it is actually generating a magnetic field which is also propagating up and down, right. So, how do you explain the generation of magnetic field? Your electric field is oscillating. As your electric field is oscillating, there is a flux that is changing, and as the flux is changing, it is inducing a magnetic field. So, that magnetic field is what is oscillating as a result of electric field. Now, in free space, the oscillation of electric field and magnetic field are in the same phase, which means when the electric field is attaining a maximum, the magnetic field is also attaining a maximum, and so on. Now, they are propagating in free space because of the wave equation. The time dependence in, or the change in electric field in time is related to the change in electric field in space. Electric field changing in time, del square E is del square E by del T square. So, electric field changing in time is giving rise to a change in space, which is what you are seeing. And of course, the consequences, the electric field and magnetic field are orthogonal to each other, and the wave is propagating along the third orthogonal direction. So, like this, if you go, I am sure you have lot of electromagnetics to learn, and these are some of the simulation tools or simulations or animations in as Java applets, which will help you to visualize the electromagnetic field and understand it. Okay, so this was battery down on the transmitter. So from which point should I repeat? Can you please somebody type? Can somebody type in the chat window from which point should I repeat? Repeat the example from start. Okay. So first I showed you an example of electromagnetic wave propagation. This is from this very useful Java applet site, which is Amonagawa, AMANOGAWA, Amonagawa. So what you see in the red is electric field, in the blue is magnetic field, and you see that the red and the blue are orthogonal to each other. So we are trying to explain to you how an electromagnetic wave is generated, and to generate any wave, it has to comply with the wave equation, which means that you see, I need to have a time dependence. If I don't have a time dependence, I don't have a space dependence. Okay. So somebody is asking me to repeat the website name. I think that is given as a course material, so you can please go through that. I can write it down also. So one of the website is PHET and the other one is this one, AMANOGAWA. This is from the University of Colorado. These are the websites. Okay, so let's get back to that. So what I was trying to tell you was, unless I have so unless I have a time variation, I cannot have a space variation. So the time variation is introduced here at a specific frequency f. So I have a frequency f, which means that my electric field is oscillating at a specific frequency. Now as my electric field is oscillating, my Ampere's law tells me that an oscillating electric field will produce a time rate of electric flux, and time rate of electric flux has to produce a magnetic field. So that's why you have a magnetic field that is oscillating. The same thing we saw in this simulation also. When we wiggle the electron, right, you are just changing the electric field. When you are changing the electric field, you could actually get a magnetic field also in a direction perpendicular. What I want you to notice is that in this specific case, the electric field and magnetic field oscillation are in phase, and the rate at which it is propagating in space is given by your wave equation. Your wave equation actually tells you how the field is propagating in space. You have many electromagnetic wave related simulations, electric and magnetic field, for example, in a parallel plate waveguide is here, right. This is a waveguide which actually shows the electric and magnetic field. I can turn on, I can select the modes, and so when you, I mean, these are things which will be useful for instance, this is the mode of the electric field of inside a parallel plate waveguide, inside a rectangular waveguide. Now you see that the red represents large field, blue represents small field, and you see that across the cross section, let us say you started with an electric field in this direction, the field is reducing to 0 at the edge, and that is because you have metal sitting in the edge, and you can actually interpret in terms of boundary condition, which we will do in a minute. So, these are just to show you some of the examples of simulations that are available. So, I would request you to actually go back and take a look at some of these things. There has been a lot of maths since the beginning of the class today. Let us now move to magic, and this is the magic that I am showing you. What you see here is not ghosts. These are people standing with tube lights, and the tube lights are glowing without any connection to electric current. Okay. So, these are people who are standing and holding tube lights like this, and the tube light is glowing. Okay. I will show you another picture here. This is a farm. Okay. In this farm, you are seeing tube lights which are mounted, just dug and kept, or rather it is just kept vertically, and you see that these tube lights are glowing on their own without anybody sending an electric current through it. The question is, why do you think the tube lights are glowing, and what is the physics behind it? It is not magic, it is only physics. We are going to work out this as a problem, as a numerical problem, where I am going to work out the tube light magic. In both these examples, if you noticed carefully, above the tube lights you have power transmission lines running. You see the power transmission lines are running above the tube lights. Even in the other picture you saw that there is power transmission line above these tube lights. So, definitely this physics has to do with something to do with the power transmission line, but you see they are not physically connected. The power transmission line is above the in sky, or rather at a height. The tube lights are somewhere close to the earth, but then there is something that is really happening in the system. So, what I will do is I will let you think about this. I will open the class for questions now, and when we come back, I think you would have thought about this, and then we will solve this tube light magic problem. So, let us open the class for questions. If you have any questions on any of the content that you learnt, or rather I taught, I do not know whether you learnt, please come up with your questions, because we are going to do the tube light problem solving immediately after this. So, please start asking your questions. I will wait for 2 minutes before starting this. This question is, why does a tube light glow when it is held under a power transmission line? I don't know if you have tried this, but it works. So, I'll wait for a minute for questions, if any, up to this part, then continue solving this problem. Okay, so there's a question. Why do we make the assumption that H tends to 0 during boundary condition derivation? So, the reason why we make assumption is we want to know what is the value of electric field at the boundary. So, the way you reach the boundary is by collapsing that surface or the line to the boundary. You are going to the limit of the boundary. So, earlier you had the coil this way. Now, the way you can, and the boundary is somewhere in between, the way you can reach the boundary is to keep them closer such that the H tends to 0. So, that is the reason why we have to make that assumption. Okay, there is a question on skin depth. I don't think I will be able to explain that because that requires a little more further understanding of electric field and magnetic field in a material medium, which is not a part of this syllabus. So, if I were to talk about skin depth, it will be in another course. Okay, what is the significance of Helmholtz equation? It's a very nice question. Why should I work with an Helmholtz equation? The reason why we are looking at Helmholtz equation is because now I have differentiation only in space. Okay, it's a second order differential equation, but it's a linear differential equation in space. I don't have to worry about del by del t, and I can calculate the electric field at any omega. Now, if I remember my Fourier theorem, any arbitrary time dependence, once it is repeating, I can write it, I can represent it as sum of multiple frequencies. So, I can have my electric field with any random frequency content, but I can represent it as a sum of linear combination of multiple harmonic frequencies, and I calculate the response of the medium, or I calculate how the electromagnetic field is propagating in the medium at a specific frequency. I can do that for all the frequencies because my equation has omega in it, and then I take the total response as the sum of the responses. So, that is why we always use Helmholtz equation in electromagnetics. And the reason why we are able to do Helmholtz equation is because superposition works, and superposition works because this is a linear differential equation. This equation is linear differential equation. It's a second order, but it's a linear equation. So, it means that if I get a response for a frequency omega 1, get a response for a frequency omega 2, the total response is the sum of the individual responses. That is essentially saying why superposition works. So, we always use Helmholtz equation for solving any electric field, magnetic field problem. What is the significance of relationship of permittivity with normal component of electric field? So, we will work out a problem which tells you that it is the permittivity of the medium which makes the field bend. So, if the tangential components and normal components were identical, then the electric field in both the media would look the same. It simply says that the response of the medium to the electric field is your permittivity, and that is deciding how the field is bending. So, that is the physical significance. Okay, if there is no other question, let us start solving the tube light problem. So, let us get some specific details. Power transmission line is a 3-phase line, which means that there are 3 conductors. It is mounted at a height of 16 meter, mounted at a height of 12 meter. They are 16 meter apart. Effective diameter is 0.6 meter, and the bulb is held at 2 meter above ground. Okay. So, the question is, I can draw the picture. These are the 3 transmission lines. I am just drawing the cross section, and mind you, their potential difference is very large. Its potential difference is between the 2 cables in a 3-phase line. 3-phase line, so you have 3 cables, and the potential difference is something like 750 kilovolt. And this length is 16 meter. This diameter is what is given as 0.6 meter, and this whole thing is at a height of 12 meter. My tube light is here. So, obviously, the tube light will, how does a tube light glow? The tube light glows because there is some phosphorescent material inside, and once you have ionized the gas inside the tube light, it generates ultraviolet that goes and hits the coating, and that's what is giving you the light. So I need to somehow ionize the gas inside the tube light. The way we ionize gas inside the tube light in regular tube lights like this is by applying an electric current. But by applying an electric current, I am actually creating an electric field. So if the tube light is experiencing an electric field, that is enough for the tube light to glow. So how is that experiencing an electric field? So can you connect me to some other college? So I am expecting some electric field in the tube light because of the 3 transmission lines. Now I am trying to calculate what is the net electric field. So the electric field, let's mark this as transmission line 1, transmission line 2, transmission line 3. Okay. Now due to transmission line 3, at this point I know that the electric field is in the downward direction. Due to line 2, it's along this line and it's at this angle. Due to line 1, it's along this line at this angle. So I have E3, I have E2, I have E1. So I basically have 3 electric fields that are acting on this point. So this is the point P where I have the tube light. Now I have enough geometry to calculate what are these heights. The total height is 10 meter. So from this height, from this point of the tube light to this is 10 meter. Total is 12. So this is 2. And I know the spacing between them. This is 16 meter and this is 16 meter. So I can calculate this as 18.9 meter and this as 33.5 meter by applying Pythagoras theorem. I can also calculate the angle between this. So essentially I can calculate this angle and this angle, and those would be the angles corresponding to this. So I can from this triangle I can calculate all the possible angles. Point I want to calculate is, so the approach is going to be the following: find the total electric field due to the 3 lines. How am I going to find the total electric field? If this is the horizontal, the E3 is in this direction, E2 is in some other direction like this, E1 is in this direction. Let's say this is making an angle theta 1 and E2 is making an angle theta 2. I have enough information to find out theta 1 and theta 2 from this triangular geometry. So I am going to calculate what is E1, E2 and E3. And essentially write the component of E1, E2, E3 along the x and along the y axis. So I'm going to do that. Let's say this is my y axis, so I can this is my minus y direction, E3 is along the minus y direction. But to be able to do this, so the total electric field is E1 plus E2 plus E3. So this example I have picked in such a way that it can illustrate multiple of the concepts that we learned. So to be able to calculate the electric field, I need to basically calculate the electric field due to a current carrying conductor. So I have a current carrying conductor, right? And I know that the electric field is directed outwards. This is not magnetic field, this is electric field directed outwards. So to find the electric field directed outwards, I am going to use Gauss law. So this is my Gaussian surface. okay. And let us also define the line density, right, charge density. Let us say the charge density is line density rho L, which is essentially charge per length. I want to be calculating what is the electric field through this elemental area in the outward direction. So, I am going to be using Gauss law, which says total surface integral d dot ds is charge q enclosed. In fact, Gauss law said d dot ds. So, if I write in terms of E, it should be divided by epsilon, and if it is free space outside, it is epsilon naught. Now, how do I calculate this surface integral? So, to calculate this surface integral, I have to evaluate this integral. Charge enclosed is not a problem. Let us say this cylinder is of length L, then the charge enclosed is rho L times L divided by epsilon naught. But how do I evaluate this surface integral? So, if I look at the problem, I am just exaggerating this. This is a cylinder around, and I am going to find out what is the electric field at a distance r. Let us say this is my origin. I want to find out what is the electric field at a distance r. So, the radius of the cylinder is r. As I keep going farther and farther and farther, I will keep my cylinder, making my cylinder bigger and bigger and bigger. First of all, let us calculate ds. ds is outward normal. So, ds has a direction which is AR in the cylindrical coordinate, because it is in the outward normal direction. Cylindrical coordinate, we know that r is the radius of the cylinder. What about the area of the cylinder? So, it has a length dimension and it has a width dimension. Now, the width dimension, how do I get that? It is the length of this. So, I have an elemental angle d phi and an elemental length dh. So, this elemental angle d phi tells me that the length of this elemental arc is r d phi. This is r d phi, and this height is dh. So, this is how I calculated my surface ds. What about E? E has an r dependence and its direction is outward normal. So, it is AR. So, the total surface integral E dot ds is nothing but surface integral ER AR dot R d phi dh AR. This is the left hand side. Now, AR dot AR is 1. What would be the limits of the integral? So, as I move this area around, what changes is the angle. So, one change is phi, and that angle varies from 0 to 2 pi, because I am covering the entire cylinder. For a given cylinder, and I am moving this ds along the surface of the cylinder, because I am moving it on the surface of the cylinder, the r does not change. That is a constant here. What I would change, what could change is, I could pick this area at a different height. So, the next variable here is h, 0 to, and height goes from, I already assumed that this is length L. So, h goes from 0 to L. This would mean my phi is going from 0 to 2 pi. So, integration over d phi, there is no other term which depends on, so that gives me 2 pi. There is no other term which depends on h but for dh, so that gives me L, and AR dot AR is 1, and so you have ER, which is a constant as far as d phi and dh is concerned. This ER is function of only R. So, this is my left hand side. Right hand side I already have. So, now if I equate this, 2 pi L E, which is a function of R, is rho L by epsilon naught, which means ER is a function of R, your L cancels out, is rho L by 2 pi epsilon naught. So, this is an expression for the electric field due to a charged wire. Okay. How are we going to use this now? I am going to use this to calculate the electric field at this angle, at this angle and at this angle. So, I can just substitute in this expression. There is one problem, I do not know the value of rho L for this transmission line. I do not have the information for rho L. I know what is epsilon naught. So, I can calculate if E3 is the electric field due to this conductor, I can calculate, well, I made a mistake here. What the mistake I made is this ER, I should have this R here. I forgot this R. There is this R. So, there is an R here, there is an R here, it's an R here. It's important to have that R because otherwise electric field will be a constant. That's not the case we know. So, if I calculate if I want to calculate E3, I know what is the value of R here. So, I want to calculate electric field at this point, I know what is this distance, I just substitute this distance, but I do not know the value of rho L. So, I have to calculate rho L. What other information do I have? I have the information that the potential difference between two wires is 750 kilovolt. So, between the two wires, between the two transmission line cables, between the two cables, so this is the first cable, this is the second cable, I know that this center to center distance is 16 meter and I know that the potential difference is 750 kilovolt. So, one of them is ground line, one of them is high voltage line and the difference in potential is 750 kilovolt. I need to use that information to carry, so this is the line that is carrying the voltage or carrying the electric current. I am going to use this information to find out what is rho L. How do I do that? I use Faraday's law and I demand that line integral E dot dl, well, I do not really have to use Faraday's law, I basically have to use the definition of voltage. I told you the other day that when you say potential, it is a work done by unit charge. So, that is E dot dl minus E dot dl. Okay. So, but then you should know how to apply this E dot dl. I am talking about two current carrying conductors and I am talking about the potential between them. I know what is the electric field due to the current carrying conductor, we just derived that. But in order to do this potential, I need to know in which direction should I apply the loop integral. Now, potential is the work done by unit charge to move from infinity to that point, or potential difference is the work done in moving a unit charge from one point to the other. So, it simply says that if you want to move a unit charge from this point to this point, you need to do a work which is corresponding to 750 kilovolt. So, the dl that I am talking about, the path that I am talking about is actually here, it's actually the path is this. So, the dl that I have to look at is actually a elemental length like this. Okay. So, this means that if I were to apply this, my E is, we have already derived what E is. E is, it has ER in the AR direction, okay, and DL is also in the radial direction. So, my DL is actually dr. So, in the cylindrical coordinate system, this is my cylinder, my dr is along this direction. It is a radial direction because the path that I am taking is along the radius. So, it is dr, which I can write as magnitude of that in the AR direction. So, your voltage is nothing but ER AR dot dr AR. Now, what is the limit of this integration? I have to change this dl from this point to this point. So, dl has to change from this point to this point. I know this point, if I keep this one as, so this center to center, the spacing is 16 meter, which means that this limit of integration would have r varying from 0 to, in fact, if I take the edge to edge, it will be 0.3 to, if this is 16, it will be 15.7. I do not take center to center simply because inside the conductor there is no electric field. So, there is no concept of potential inside the conductor, but outside. So, the potential is starting from, or electric field is starting from outside the conductor. So, from that point of view, I take this. If I perform this integration, I know the left hand side is 750 kilovolt and the right hand side, these two dot products will give me 1. So, I get ER, I have already derived what ER is, it is rho L divided by 2 pi epsilon naught R. So, now R is inside my integration. So, R is 0.3 to 15.7 and R dr, or sorry, that R is in the denominator. So, it should be dr over R because EL is rho L by 2 pi epsilon naught R. Now, this would be 2 pi epsilon naught ln of R, which goes from 0.3 to 15.7. So, the only unknown here, so this is rho L divided by 2 pi epsilon naught, ln of R would mean that it is ln of 15.7 divided by ln of 0.3, sorry, ln of 15.7 minus ln of 0.3. So, the only unknown here is rho L, because I know my left hand side is 750 kilovolt. So, I can calculate my rho L as substitution of all this will give me 10.76 microcoulomb per meter. You know that coulomb is a large unit. 1 coulomb means lot of charge, which is why even with 750 kilovolt of potential difference, the line charge density is only microcoulomb. So, now I have rho L. Once I have rho L, I can go back to my original problem. So, these were the 3 conductors. I can now calculate what is the electric field due to E3. I can calculate what is the electric field due to E2, and I can calculate what is the electric field due to E1, provided I know these angles. So, E3 is along, so the magnitude of E3 is along the minus y direction. This is y, this is minus y. So, I fix a minus ay. And what is the magnitude of E3? It is given by rho L divided by 2 pi epsilon naught R, and rho L is 10.76 microcoulomb per meter divided by 2 pi epsilon naught R. Now, this distance is 10 meter, this is 2 meter. So, this R is 10 meter. So, this would work out to be, if you put in the values of these numbers, this will work out to be minus 19.6 into 10 power 6, and we are writing electric field. So, this much volt per meter in the AY direction, minus AY direction. This is E3. Now, what about E2? To do that, we need to calculate this angle theta 2. I calculate that angle from my triangle, and that theta 2 turns out to be 32 degrees. Okay. So, I can calculate E2 as 10.76 microcoulomb per meter divided by 2 pi epsilon naught. Here it was 10 meter, corresponding to E2. I already told you what was a calculated value. That was something like 18.9 meter. So, this is 2 pi epsilon naught into 18.9 meter. Okay. And cosine of this component would be along AX plus, so this is the magnitude, cos component is along AX, and the same 10.76 microcoulomb per meter divided by 2 pi epsilon naught into 18.9 meter into sine of that theta 2 is along minus AY direction. You are just writing it as two components. This is actually minus 5.4 if we work out AY plus 8.66 AX. All these things would require a calculator for you to do the calculation, and this is into 10 power 3 volt per meter. Sorry, this 19.3 into 10 power 3. Similarly, you can calculate E3. You can find out E1. You can find out this angle. That angle turns out to be theta 1 turns out to be 17.4. This angles can be calculated from the geometry of the problem. It's just, you know, sine theta is opposite side by hypotenuse kind of calculation. So, this E1 again you can resolve into x and y components, and that answer will turn out to be minus 172 AY plus 5.5 AX into 10 power 3. So, now you have E1, E2, E3 and the x and y components of each. So, the total E is simply you add the x component, y component, and I take the magnitude of E as, so I can calculate, I can add up all this, and that will work out to be, if I calculate the magnitude of all that, that will work out to be 23.6 kilovolt per meter. So, this is the point. The point is, the reason for the magic we saw is because I have 3 transmission lines. Even though the 3 transmission lines, the electric field due to the 3 transmission lines are in different directions, at this point where I am keeping the tube light, this is the net electric field, 23.6 kilovolt per meter. That is the next net electric field. So, if the tube light had a length of, let us say 0.5 meter, okay, potential across that is very large, and that is enough for the tube light to glow. Well, we do not get a shock by standing there simply because our body is largely insulating, and or the see what would matter, when do we get a shock? We get a shock when there is a large current passing through our body. So, if we allow a large current, which means for some reason we have a conducting path, this 23.6 is enough for us to get a shock also. But typically just in free space, turns out that about 25 and above is what is the limit for human beings. But this voltage is sufficient for the tube light to glow. So, this is why you are seeing all these tube lights glowing, just because you are standing under the transmission line. Do not try to do this experiment under the 230 volt line, you will not get anything. You got this large number only because this was 750 kilovolt. So, this kilovolt was important. This kilovolt is what is giving rise to this kilovolt here. If that is not the case, you will get something at 23 volt. Okay. So, you are still inducing some electric field, and if it is a 60 hertz line, it is continuously oscillating. So, which means that you are getting some induction, electromagnetic induction at 60 hertz at that point. This is the reason why you have electromagnetic induction. You do some experiments in high frequency experiments in the lab. Sometimes what you find is that you will have a noise which corresponds to 50 hertz. And the reason why you have that noise corresponding to 50 hertz is because you will have electric cable which is carrying electric current at 50 hertz. That is producing, you see, it is producing at a distance, it is producing an electric field. And if this is oscillating at 50 hertz, this is also going to oscillate at 50 hertz. So, if you are trying to run an experiment with 50 hertz, or rather with some frequency here, this 50 hertz will appear as a noise, because it can induce a voltage and it can appear as a noise. So, that is this example is also telling you that the reason for electromagnetic induction, right. I was talking about energy harvesting sometime. This example is also telling you that you can induce electric field at a distance, which means you can have energy harvested. Essentially, the power carried by the transmission line you are utilizing to have the whole place lit up. One more last important consequence I want to talk about boundary condition is that, which you will keep using over and over again. Let us say this is metal, or let us say this is conductor and this is dielectric. Essentially, I have air and a conductor. Now, in a conductor, sigma is infinity. So, conductivity is infinity. Electric field has to be 0 because electric field is J is sigma E. So, your electric field inside the conductor must be equal to 0. One of the important consequences of this is that because it's a if your medium is a perfect conductor. If the medium is perfect conductor, so it simply means that electric field inside the conductor is 0. There cannot be a field inside the conductor, because that would mean that you have inside the conductor without any, the free charges would be moving around. That is not the case. So, if I try to apply boundary conditions here, I know that E1 tangential minus E is equal to E2 tangential, and epsilon 1 E1 normal is equal to epsilon 2 E2 normal, which means near the conductor metal boundary, at that point the tangential component inside is 0, which means the tangential component outside should also be 0. The electric field here cannot have a component like this. The normal component inside is also 0, because electric field inside the conductor is 0. So, you would have E1 epsilon, so which would actually mean that, well, I have to rewrite this one cannot give. So, epsilon 1 E1 normal component, if you look at the boundary condition, go back and look at the boundary conditions, this is my boundary condition. Epsilon 1 E1 normal minus epsilon 2 E2 normal is rho s. And this is 0, which means that I have E1 normal, which is equal to rho s by epsilon 1. I have only normal component, my tangential component is 0, which means that if I have electric field in a medium, let us say like electric field in a medium at an angle like this, which means it could have a tangential component, normal component, and so on. And let us say I keep a metal here, this is a metal ball, solid metal ball. Obviously, I should not have electric field inside this. Obviously, I should not have electric field inside this. So, in the presence of the metal. At every point on the metal surface, I should not have tangential component. I should have only normal component. So what is the normal to this surface? I should have this. I should have this. I should have this. I should have only the normal component. So how is my electric field, which was like this? Let's say this was the electric field. What happens is that when it reaches near the metal, it actually turns. It turns like this. Goes like this. This is very one interesting consequence of when it is not near the metal. So this is metal. When it is not near the metal, the electric field is as per the direction otherwise. But if you keep a metal there, it simply means that the field naturally turns because it has to satisfy the boundary condition. Another interesting consequence is if I take a capacitor, let us say I have a parallel plate. This is metal 1, this is metal 2. How do I draw the electric field between them? It is very easy because I know that between at the surface of the metal, the electric field has to be normal. So if this upper plate is at higher potential, my electric field is this. But what about the electric field at the edge? At this part also the electric field has to be normal. So it has to turn like this. It should start turning like this. So you do see an electric field even just outside the capacitor, and the direction of that electric field can be very clearly predictable, and that is what is called as the fringing field of capacitor. Or in other words, if I imagine that these are the two plates of a microstrip line. On a PCB you are having a top plate and a bottom plate with which you are applying an electric field. You will see that there is an electric field leaking out, and this leaking out of electric field is simply to maintain the boundary condition. So you would definitely get some energy at the output. What's the problem with that? The problem is if this is oscillating, if this electric field is having a function of time, it means that there is a magnetic field that is produced as a function of time. It means that you have to satisfy the wave equation. It means that the wave is propagating, which means that in a neighboring piece of wire you will get electromagnetic induction. So you are coming back to the EMI problem again, right? So these are some of the practical consequences of electromagnetic wave propagation and the boundary conditions. I think we close now. There is a bunch of tutorial problems and multiple choice questions which I have circulated. I would request the teachers to use that for evaluating or for working it out as tutorials. The class is now open for question, and before I close, I again repeat that this has been a one-way communication, and I am not sure whether I was entirely happy with this communication, but if there are any questions, please send an email at regarding any specific questions in electromagnetics, or regarding the books that you want to use, regarding the sources for simulations, whatever it is. If there is a question, please send me an email. So thank you. I'll open the class for questions. If there is anything, please. Okay, what is the importance? It's just to show electromagnetic induction. There's nothing else. Okay, so if there are no more questions, I will close the session, and thank you. you.